So thanks to the organizers for giving me this opportunity to talk in this in-house. This is my third time talking in the in-house, probably last. So I'm going to tell you something about this Hertz-Debye formalism in D-sitter. And Hertz-Debye formalism, you guys might know, is a way of solving electromagnetic field equations. Generally, we study this in flat space in our textbooks, but what I'm trying to do is to apply this formalism to D-sitter. And this is a part of a work that I've been doing with my advisor, Loga. And so let me get started. So, you guys all must have seen this image of the evolution of the universe, this timeline of the universe. And in the early part, as well as the late part, something called the dark energy gives a lot of, affects a lot of the physics. And this dark energy in inflation in the form of rapid expansion, it plays a role. Similar rapid expansion is given at the later time of the universe because of this dark energy. And so what I'm trying to understand is there's a lot of physics that goes on in between of structure formation, of galaxies, of stars, and so on. But what I'm trying to do is sort of idealize the problem by getting rid of a lot of this interesting but messy stuff. And I just want to study an idealized problem where I only have a purely dark energy universe. And in this universe, when you have matter or radiation, those things in an expanding universe will dilute away. But dark energy has this property that it doesn't dilute away. And this, because of this, if you take a purely dark energy universe, what happens is you get a time reversal symmetry, which other like more complicated expanding universes don't have. And so it is a nice idealized system to study. Now, the metric of D-sitter looks kind of like this. The only reason I write this is to tell you about this particular factor, which will keep on occurring in the later parts of the talk. So other than this factor, the metric pretty much looks like flat metric. So if I put this h, which is what is called the Hubble's constant, which in D-sitter is actually a constant, unlike our real universe where the Hubble constant actually changes. This constant will play a role, and if you put this to 0, you'll notice that the metric just becomes flat space. So the Hubble constant, in some sense, controls how much you deviate from flat space when you have dark energy. Now, in a universe like this, if you're sitting in a dark energy dominated universe, what happens is everything around you behaves as if it's in an inverted potential well. That is, like, because it's expanding, everything farther and farther away from you will go further away from you at faster and faster rates the farther they are. So if they are closer by, they are going away from you at some rate, but if they are farther than that, then they are going farther away from you at a faster rate. And so it is kind of like an inverted harmonic well. And what this gives rise to is this particular phenomena where if something is so really far away, the light coming from them to us, because the space in between is expanding, doesn't quite reach us all the time. And so the boundary beyond which no light can reach us is given by this horizon, which is at 1 by h value. Okay, so now what I want to do is I want to study electromagnetic waves in this universe, and in particular I want to study electromagnetic radiation. So what does the cosmological constant, what does this Hubble expansion do to the electromagnetic radiation? That is the question. Now, in flat space, generally, when we are asking for radiation, what we do is we demand that there's some localized source, and far away from that source, the waves have to be outgoing. As in, with time the R increases. So they are of this form. And in de-Sitter, what we will do is similarly we'll demand that instead of at very large R, we'll just demand that because there is a horizon, we'll say that at the horizon, the things are going out and nothing is coming back from the horizon. That's a very natural boundary condition to put. Now, I actually want to solve the electromagnetic equations of motion, and so I will do that in a particular formalism, and now I'll try to explain what this Hertz-Debye formalism is. So, in what we will do is, we'll actually decompose, so because we have electromagnetism, we have it is sourced by a 4-vector current, and what I will do is, I will decompose that 4-vector into things. There's a charge density, which is the T component, there is a radial component, and then there are spherical components. So there is a charge density, there is a radial component which comes out of the sphere, a current which comes out of the sphere, and then there are tangential currents that go along a sphere, right? So what I will do is I will decompose each of these into spherical harmonics. Now, because charge density and the radial component is in the space of the sphere, they are like scalars, I can just decompose them into YLMs, which are usual spherical harmonics, but the tangential currents are vectors on the sphere, and so they can be decomposed into, as we heard in the last talk, two different kinds of spherical harmonics. One is given by just a derivative operator acting on the YLMs, which is like del theta and del phi acting on the YLMs, and the other component is given by this R cross grad acting on YLMs. Okay, so these are the two spherical vector spherical harmonics on the sphere. Now, the reason to do this is because if you take tangential currents which go like this, and this was mentioned in the previous talk also, that this vector is a divergenceless vector, and so this the current which goes along with this spherical harmonic is conserved by itself, whereas the three other components are tied together by some conservation equation. And so the point of this decomposition is that this sector of the current which goes along with this spherical harmonic, vector spherical harmonic, completely decouples. So you can write down a separate set of equations for these currents and a separate set of equations for the others. And so let me move on, I'm going too slowly. You can do a similar thing for the gauge field, and in the gauge field again you can decompose the T component and the R components in terms of YLMs, and what we do is we choose a gauge in which the theta and phi only have the R cross grad spherical harmonic, and you can, once you do this, you have these two scalars. You are basically left with two scalars. One that goes along with this R cross grad theta of YLM, and the other one which comes in the T and the R component. And you can see that this choice of scalars is actually consistent with the electromagnetic equations, and this you can only do in the absence of sources. Okay, so the point here is that there is a different parity of this phi E and phi B, which is what decouples these two, and the phi B will now only talk to these currents, the ones which come with R cross grad, and they won't talk to the other sources. And so you can actually completely decouple them and write down equations for both, and it is a thing in particular in d-Sitter 4-dimensional d-Sitter, what happens is that they both satisfy the same equation of motion. So now all you have to do is just solve this scalar equation of motion, and you're basically done with the problem outside the sphere, outside the sources, because you wrote down the potentials in this form, and now you just solve the equations for the potentials. And you can solve for outgoing waves, and in flat space, these outgoing waves are just outgoing Hankel function. In d theta, they become some 2f1 hypergeometric function. Now, in presence of sources, what happens though? Because of the gauge constraint, you can't actually use the same decomposition that you used before. But the problem is not very different in the sense that you can sort of modify your gauge choice by adding these source dependent terms. And once you have done this, the problem is solved. This is sort of consistent with the electromagnetic equations, and you can actually just work with these source moments. Now, these rho LM and JR LM are just the coefficients of the YLM expansion of the sources. Okay, and once you write this down, you actually get the inhomogeneous equations for these fields, and that allows you to connect your moments to your radiation. How a particular source radiates. And so you can then again solve these equations how you would solve any inhomogeneous scalar field equation. In flat space, the Green's function is given by a product of Bessel function and Hankel function. Similarly, here it becomes some 2f1 hypergeometrics, two different kinds of 2f1 hypergeometrics in d theta. Now, I'll just finish, give me 30 seconds. The main point, I just illustrated like a very simple example of this formalism, but the power of this formalism is in its applicability to many different scenarios. One thing is that you can do it for arbitrary dimensional d theta. There are certain new things that happen, like there are new kinds of vector spherical harmonics that we didn't see in d theta 4. But other than that, you can actually do it for any general dimensional d theta. You can actually also use it, use a similar formalism for linearized gravity, where you actually decompose the stress tensor into, again, spherical harmonics and vector spherical harmonics. But again, here you will also get tensor spherical harmonics on the sphere. Now, and this formalism actually you can apply to many other kinds of spacetimes where you can decompose it into radial. There is a radial coordinate which says how far you are going from the source. There is a time, and then the rest of it is a symmetric space like plane or a sphere, etc. That's it.
Questions?
I have this question about H, the Hubble constant. How do you decide what constant it is? And since we cannot measure, I mean, in our universe we do the measurement. So
Yeah.
what constant do you take in your case?
I just take a constant. I don't actually input values. But if you are asking what is the corresponding like number for our universe,
Yes.
In length units, it's about 45 giga light years.
No, okay, fine. And how does this thing help us understand our universe better, this work?
Well, there's a couple of things actually. You can obviously ask this question about like, are there really long-range electromagnetic fields which this will help? It is not completely clear, but one thing is just even if it doesn't help us understand the source moments, it helps us understand the propagation. Like when electromagnetic waves travel far away, they are affected by the Hubble constant, like the electromagnetic fields coming from the CMB and so on.
Okay.
But there's more to it in that this you can actually apply to gravity also and study, use it to study more like structure formation and so on, which actually takes into account effects of the cosmological constant.
Okay, thank you.
Any questions? If not, then thanks, Omkar, once again.